Hello, everybody. As promised, I would like to help work on this problem again. This was the handout provided to you during your lecture, which you worked on, and I went really fast over it. So here, a 70 kilogram person slides down a frictionless water slide. The height of the slide is 20 meters. What is their velocity when they reach the end of the slide? Okay, so you can start with this equation, which is work done. We're talking about conservative forces. Work done equals to E mech equals to change in kinetic energy plus change in potential energy equals to 0. So if you rewrite this equation, okay, this will be K1 plus U1 equals to K2 plus U2. 1 being this position here and 2 being this position here. So at position 1, okay, the kinetic energy is 0 because person starts from rest. If you consider this height to be 0 here, potential energy at 2 is 0. So rewriting this equation, mgh equals to 1 half mv2 squared, height 1, mass cancels out, so v2 is square root of 2g height 1, which is 19.8 meters per second, or v is approximately 20.0 meters per second. Now in the second part it says, now let's say at the bottom of the slide this person lands in a mud pit and the coefficient of kinetic friction between them is 0.4. The person lands in the mud slide at the stop, from the starting at the top of the slide. When they come to stop, how much work is done by gravity, normal force, friction? How far from the bottom does the slide, does the person stop? Is the total energy conserved? Where did that energy go? All right. So gravity just does a, like if you just on the slide itself, okay, on the slide, okay, there's a force, gravity acting on the person, okay. There's a normal force too, okay, which is perpendicular to the displacement, direction of displacement, so that is 0. Work done by, but however in this, when it comes to this point here, I'm gonna draw this person as a box. Force gravity, sorry, force normal, force gravity, okay, person is sliding that way, so the friction kinetic is going to be in that direction. So if you rewrite this, okay, gravity just does work on the slide over there. Okay, when it's in that mud pit, gravity is perpendicular to the displacement, so gravity does not do any work. Normal does not do any work. Friction is bringing it to stop, so friction kinetic is doing a negative work on the person. So work done by gravity is force gravity times the displacement, which is the height, so mgd, that is 70 kilograms times 9.8 meters per second squared times the height of 20 meters. That gives 1.37 times 10 to the power 4 joules, which is also 13,720 joules. So work done by force normal, d cosine of 90 degrees, which is 0. So work done by friction is friction kinetic, d cosine of 180 degrees, right? So that is mu k mg d. So cosine of 180 is negative. Okay. So work net is change in kinetic energy, which is kinetic final minus kinetic initial. So just in that mud pit, whatever the initial velocity it had is lost, okay, and which is due to friction. So friction does the net work, which is negative mu k mgd. K final it comes to rest, so that is 0 minus k initial, so my negative goes away. Mu k mgd equals to 1/2 mv initial squared. So v initial is the initial right at the bottom of the slide. So from that you can find d. So d would be v initial squared, or the other way to write that v is v2. That's what we calculated earlier. Okay, 2g mu k, which you get to be 50 meters. Similarly, if we use that conservation of energy equation, since there was thermal energy and friction involved, so we can write that as a thermal energy. So work done equals to change in E mech plus change in E thermal equals to 0. If you rewrite this equation, you get K2 plus U2 plus change in E thermal equals to K1 plus U1. So we are just talking about this mud pit. So position 1, okay, position 2. At position 2, since we consider this height to be 0, okay, at position 2 there's no potential energy. At position 1, potential energy is 0. Potential energy at position 2 is 0 as well. It comes to rest at position 2, so kinetic energy 2 is 0. So whatever the kinetic energy initial it had is converted in the form of thermal energy. Okay, and thermal energy is defined as thermal energy gain is due to that friction here. So friction kinetic times d is 1/2 mv2 squared. So mass cancel. Oh, sorry. Let me not cancel this mass away yet. So mu k mgd equals to 1/2 mv2 squared. Mass goes away. You get d equals to v squared over 2 mu k g. The same thing as we did earlier. Okay. Less steps. Okay, just using one equation, you can get the same thing. All right. In the next one, you have the figure shows the water slide, right, in which a glider is shot by a spring. Oh, sorry. Two questions here. Is the energy conserved? Initially, there was some 13,720 joules of energy. Out of that, some of that was lost due to friction. Some of them was converted into as a the total energy is the same. Whatever the potential energy initially it had was lost. Okay, so the energy is not conserved. Okay, so some amount of energy is lost, and then whatever the energy is lost is being converted in the form of heat energy or the thermal energy. Okay, but when you talk about the total energy in the whole system is conserved. Okay, but when you're just talking about the potential energy, it's been lost. Okay, there's many ways to interpret that one. The figure shows a water slide ride in which a glider is shot by a spring along a water-drenched frictionless track that takes the glider from horizontal section down to the ground level. The glider then moves along a ground level track. It is gradually brought to rest by friction. The total mass is given, your k spring constant is given, mu k is given. Through what distance L does the glider slide? So it wants us to find this. So we can solve this problem like the same way we did earlier. However, like we can use kinetic friction and change in kinetic energy. However, we can get rid of all that steps by just using our work done equation. So change in E mech, change in E thermal equals to 0. So K2 minus K1 plus U2 minus U1 plus change in E thermal equals to 0. So K2 plus U2 plus change in E thermal equals to K1 plus U1. Okay, when you write this equation down, okay, just by putting this E thermal, it tells you a lot. Okay, so by this, whatever the initial energy you had, kinetic energy plus potential energy, you don't have the same amount of energy at the, because some amount of, when we talk about position 1 and 2 here, this is position 1, position 2 here. So whatever the potential energy that object has, okay, by the time it gets to position 2, it comes to rest, okay. So all that potential energy, all that energy is lost, which is converted into the thermal energy. So what does that imply? So that K1 plus U1 is not going to be the same as K2 plus U2, okay. All that energy is converted in terms of thermal, which is given as, so if you add this thermal energy, that should be equal. That's what this means. Or you can write this as K2 plus U2 equals to K1 plus U1 minus change in E thermal, okay. It's the same thing. So the way you interpret whatever the energy you have is, so at final, the whole energy is 0. This becomes 0 because potential energy is 0. Kinetic, it comes to stop, so that is 0. That means whatever the energy initially had, okay, that is lost due to friction, which has been converted into heat. So try to adapt this concept, okay. However, I'll just stick with this particular one, okay. So K2 is at position 2 is 0. U2 is 0. Kinetic energy initially started from rest, so that is 0. So we are left with E thermal. All that potential energy it had at position 1 is converted in the form of E thermal, right? So that is mu K times force normal times L, potential energy, the potential energy of the spring, Kx1 squared, plus it has some height, it has potential energy due to spring, and then the gravitational potential energy. So now if you rewrite this equation, so L equals to 1/2 Kx1 squared plus mgh1 divided by mu K, force normal is m times g. Okay, so you get your length to be 69.26 meter. If I put that in 3 significant figure, that becomes 69.3
That is so
meter.
nice.
So here you go, and my daughter likes that too. Okay, I think she's learning some physics. She's homeschooling right now. She loves this. She's learning more
About time.
she's learning about time right now, but this equation does not involve time at all. Okay.